Press a button on a flashlight, and light instantly cuts through the darkness. To understand the invisible process making that happen, we need to look at what's actually going on inside. But before we build anything, we have to establish the primary rule of electrical safety. Electricity can cause serious injury. Never experiment with wall sockets or household power lines. We will only use portable, low-voltage batteries for these concepts. Let's pull out the power source, the electric cell. Every cell has two specific connection points, or terminals. The metal cap at the top is the positive terminal, and the flat metal disc at the bottom is the negative terminal. Now look closely at the bulb in this animation. Inside the glass is a tiny wire called a filament. To make it glow, it needs power. Notice how the filament is supported by two thicker wires that drop down to two separate connection points, one on the metal case and one on the metal tip at the very base. Electricity requires a physical, unbroken path to flow. The current must travel from one terminal of our cell, enter one connection point on the bulb, pass through the filament, exit the second connection point, and return to the opposite terminal of the cell. If a single cell isn't enough, we might stack two together. But look what happens when we push two positive terminals cap to cap. The circuit fails. To combine cells properly into a battery, the positive terminal of one cell must always connect to the negative terminal of the next. This arrangement ensures a continuous path for the power to move. Connect this properly arranged battery to the two terminals of our bulb with wire, and the bulb illuminates. We've officially built an electrical circuit, a continuous closed loop for electricity to travel. Drawing realistic 3D components every time you design a circuit is slow and inefficient. Instead, engineers and scientists use standard international symbols. Watch how our physical circuit translates into a clean, flat schematic. In this diagram, the battery is represented by parallel lines. The longer line represents the positive terminal, and the shorter, thicker line is the negative terminal. By convention, we map the electric current as flowing out from the positive side, around the loop, and back to the negative side. Because these standard symbols are used worldwide, an engineer in Tokyo can read a circuit diagram drawn by someone in Berlin, perfectly understanding how to build or troubleshoot the system without needing to speak the same language. Let's swap out our standard incandescent bulb for an LED, a highly efficient light source. The standard bulb symbol disappears, and the LED symbol takes its place, showing two distinct wires. Here is the critical rule for LEDs. Unlike standard bulbs, which allow current to travel in either direction, an LED acts like a one-way gate. Electricity can only pass through it in one specific direction. Take a look at the long and short wires on the LED. Based on the battery symbols we just learned, where should the LED's long wire connect to create a working circuit? The long wire is the positive terminal. It must connect to the long, positive line of the battery. The short wire connects to the short, negative line. Once they snap into the correct positions, the current flows and the LED lights up. As you introduce more advanced components into your designs, simply closing the physical loop isn't enough. You have to pay exact attention to the direction the current is traveling. Let's break the wire in our circuit to create a gap, stopping the flow. If we slide a metal coin into that space, the connection is bridged and the circuit immediately lights up again. Materials that allow electricity to flow easily, like that metal coin or our standard copper wires, are known as electrical conductors. Now watch what happens when we remove the coin and place a rubber eraser in the gap. The flow stops dead and the light goes dark. Materials like rubber, plastic, and glass block the flow of electricity entirely. We classify these materials as insulators. Both materials serve crucial, opposing roles in daily life. Copper conductors carry the necessary power inside our cables, while the plastic insulators wrapping them trap that electricity inside, ensuring we can handle the cables safely without being shocked. Let's test this completed diagram: a battery, closed switch, metal safety pin bridge, and LED. Will it light up? No. The pin closes the loop, but the LED is backward. Its short negative wire connects to the battery's long positive line, blocking current entirely. Getting this right comes down to 4 core rules: recognizing standard symbols, tracking the positive to negative flow, matching LED pins correctly, and using conductors to bridge your connections. Feel free to screenshot this summary. Master these underlying principles, and you have the necessary foundation to confidently decode, troubleshoot, and build real-world electrical systems.